So here's the respiratory system. We'll talk about respiratory anatomy and some other important things, but we'll spend a lot of time on the functional anatomy here, sort of like we did for the kidney. So normally, though, like always, we'll look at the functions of the respiratory system. There are four major functions. Number one is gas exchange. Oxygen in, CO2 out, important components of that. Second thing is acid-base balance. As we said before, we've said a couple times this semester, the kidneys help regulate the acid-base balance by secreting or retaining hydrogen ion, and the lungs can do the same thing by adjusting the CO2, which acts as an acid in the blood. So acid-base balance is an important consideration. Immunity is an important consideration, right? And airborne particulates can make us sick. Again, connecting it to the coronavirus, right? We most worry about getting airborne droplets and inhaling those that are infected with the virus. And then the fourth one, which allows me to do this video, right? Vocalization. You could add a number 5 if you wanted, and that's like, we don't do it as much as we used to, but that's drug induction, right? So we used to do anesthesia with inhalation, or some people still do, certain types of recreational drugs or prescription drugs through inhalation as well, through the lungs. So those are the major functions. One of the ideas that I think is important to understand, and we've kind of talked about this, is this interdependency among systems. The circulatory system and the respiratory system help to complement each other. The respiratory system brings air in and out of the system, while the circulatory system moves the oxygen to the cells and the CO2 back to the lungs so we can get rid of it again. So they each rely on the other for that function. And, that's sort of like, cardiopulmonary resuscitation, right? It doesn't do any good to have the heart beating if there's no oxygen, and it doesn't do any good to have oxygen if there's no blood flow from the heart beating. So essential that they maintain each other. So functionally, we can look at the respiratory system and divide it up into two very distinct areas. There's different ways to do it. Oftentimes, anatomically, we divide it up into an upper and lower respiratory system. So if you see right here, you have the dashed line that tells you, right where the trachea is. Below that is the lower respiratory system, and above that is the upper respiratory system. So your mouth, your nose, your nasal cavity, what's called the pharynx, that's your throat, and the larynx, that's the upper. The lower would be your trachea and your bronchi, and your bronchi branch 23 times before they actually terminate in your terminal bronchioles, where we have alveoli, and that would be the lower respiratory tract. So your gas exchange surface is in the lower respiratory tract. However, since physiology is more of a functionally related class, a better way to perhaps divide the respiratory system up is the exchange surface versus the conducting zone. This does, though, certainly alter the way you look at the respiratory system. Easiest to look at the exchange surface. The exchange surface is any part of your lungs that exchange gas. 99% of your gas exchange occur in the alveoli, those grape-like structures, while only 1% occurs in like your respiratory bronchioles, as an example. If it's not an exchange surface, then it's conducting zone. And the conducting is, the first 20-something odd orders of branching, your trachea, and anything above that, your larynx, your pharynx, your mouth, your nose, and things like that. So the upper conducting zone is more concerned with delivering air, filtering air, humidifying air, while the exchange surface obviously is more concerned with gas exchange. So as we move down the respiratory system, right, the diameter gets smaller and smaller, right? The number of branches gets bigger and bigger, and we increase the surface area. And your lungs are probably equivalent to about a basketball court in terms of surface area, all bundled up into your thoracic cavity. Now, a couple of notes about the structure of the lungs. The alveoli are the structural functional units of the lung. So just like the nephron was the structural functional unit of the kidney, or the cardiac muscle, right, is the functional structural unit of the heart, then the alveoli are the structural functional unit of the lungs. And in terms of alveoli, there are three important cells in the alveoli. The first one is called type 1 cells. That makes up most of the alveoli. And those are your simple squamous epithelial cells. So all these little, hexagon-shaped cells that you see here, those are all your type 1s. And they are maximized for gas exchange. So there's these thin, simple squamous epithelial walls that really enhance the diffusion of gas. Okay? Scattered throughout, but relatively few, are the type 2 cells. The type 2 cells are interesting because they produce surfactant. And surfactant is a detergent that does a number of things, but it helps or facilitates breathing. It helps to lubricate the inside of the alveoli so they don't stick together. And what's really important is that it helps to lessen the work of breathing by equalizing the pressure. And so even though one alveolus might have more air than another, the surfactant equals the pressure because gas will move to an area of lowest pressure. And theoretically, you could move all the gas into one portion of your lung, which wouldn't be good. We'll talk about it later, but one of the more important aspects of gas exchange is we need to have blood flow to areas where we have gas and vice versa. So surfactant's a pretty important component. Humans don't start producing type 2 alveolar cells, though, until usually the 32nd to 36th week of pregnancy. And so if babies are born premature, they often lack the ability to produce surfactant because they don't have the mature type 2 cells. And so then they have to be ventilated until they can develop those. And that's called RDS, or respiratory distress syndrome. They use that term a lot, but in terms of premature babies, it's usually because of lack of surfactant. We have artificial surfactant, inhalable surfactant, and things like that. It doesn't work as well, but it does help until we can get babies to develop their own cells that produce surfactant. The third type of cell in the alveoli lung structure are the macrophages. And you can see a macrophage right here, and a couple over here, so little blob-looking things. And remember, a macrophage is just a white blood cell, a monocyte in particular, that has left the bloodstream and entered the tissue. So there's just respiratory macrophages, and they're important for immunity, things like that. Now, if we blow up, so if you look here, so it's this little square here, we're going to blow up. This is called the respiratory membrane. We're going to look at this respiratory membrane. And what's interesting in the lungs, the pulmonary capillaries and the alveoli are the closest adjacent cells in the human body under normal circumstances. And Fick's law of diffusion, right, will tell us that the net flux, how fast a substance moves across a membrane, is due to the concentration gradient and surface area, right? That's directly proportional, over the membrane resistance times membrane thickness. That's inversely proportional. So if we have this thin membrane, right, the membrane thickness is small, right, that means the flux is going to be great. And so there's a number of other protective mechanisms that help keep this at a small spacing. First of all, there tends to be low hydrostatic pressure within your pulmonary system. Remember that going back to the cardiovascular system, that your blood pressure of the pulmonary trunk is like 15/5. So it's not a very high pressure. Remember, the hydrostatic pressure is a result typically of the blood pressure. Since there's low hydrostatic pressure, there's low fluid getting pushed out of the capillaries into the space between the alveoli, that's the purple here, and the edge of the capillary wall, right? So this lightish blue area in the middle, this middle stripe, that's the fused basement membranes. But if you got fluid in there, that would move these farther apart and make breathing more difficult. The other thing that helps this, and it's literally called the safety factor, is there's a large lymphatic drainage in this area. And again, that helps to limit the amount of fluid here and prevent pulmonary edema, which would hinder gas exchange. So since the oxygen and CO2, the two gases we're primarily concerned about here, move directly across the membrane, as I mentioned before, Fick's law will play a role in terms of determining that. Now, just like we had the cardiac cycle, and that involved 5 particular phases, respiration also can be divided up into 5 particular phases. The 5 phases of respiration, I think of them as the way in a stepwise progression to get oxygen from the air I breathe into the cells and used by those cells for metabolism. So we will just step through these from 1 through 5, and again, logically makes sense to do that. So the first phase of respiration is called ventilation. Ventilation is the exchange of gas between the atmosphere, that's what the ATM stands for here, and the lungs. Okay, so that's movement of oxygen into your lungs and movement of CO2 out of your lungs. So that's called ventilation. The next one's the one that's hard for students sometimes, because if you think about it, it makes sense. But if you don't think about it hard enough, then you think, okay, why would that be true? So it's called external respiration. The reason why it's called external respiration is if you open your mouth, then the inside of your lungs are technically continuous with the outside air. So external respiration refers to that. And so that's the gas exchange between the alveoli and the blood. So that's right here. So you see oxygen going into the blood and CO2 going from the blood into the alveoli. So that's called external respiration. And again, that's because we're open to the atmosphere with our alveoli if you went kind of straight through. The third phase is called transport or gas transport, and that's moving the gas from the capillaries in the lungs to the capillaries in the tissue, and then from the capillaries in the tissue back to the capillaries in the lungs. So it's called transport. The fourth step is internal respiration. So internal respiration is the exchange of gas between your blood and your tissues. So oxygen goes typically from the blood into the tissues, and CO2 comes from the tissues into the blood. Okay? And then once we get the oxygen into the cells, then we have cellular respiration, and that's where in metabolism we use oxygen in order to make energy, and then have CO2 produced basically in its place. So 5 phases of respiration: ventilation, external respiration, gas transport, internal respiration, cellular respiration. Now we also have some gas laws to talk about. There are a couple gas laws we're going to be mostly concerned about, and some of these come from the ideal gas law, and a few of them come from other things as well. The first law we'll talk about is Boyle's law, and Boyle's law tells us pressure is equal to 1 over volume, or P equals 1 over V. Basically, it tells us pressure and volume are inversely proportional. Now, technically, you need a constant temperature, and this all comes from the ideal gas law, PV equals nRT. Don't worry about that, but worry about Boyle's law. And basically, tells us as the volume gets bigger, then the pressure gets smaller. And again, that's how we can ventilate our lungs and move air from the atmosphere into our lungs and vice versa. So in order to move air from the atmosphere into my lungs have to have a lower pressure than the atmosphere. To make the lungs have a lower pressure, what I do is I take my diaphragm, that's here on the bottom, right? And my diaphragm drops down. That increases the length of my thoracic cage. At the same time, my external intercostal muscles are contracting. And what that does is it causes the chest to go out and forward at the same time, and effectively increasing the volume of the thoracic cavity. Since the volume went up, Boyle's law tells me that the pressure is going to go down because they're inversely proportional. And now the pressure of the lungs is less than the pressure of the atmosphere, and gas moves in. So if you see these kind of subtle, these blue arrows, right, they're going into the lungs. So that's inhalation. Now for exhalation, the elastic recoil from the diaphragm and the external intercostals snap back into place. They actually give you a smaller lung volume than you started. That's what this dotted line here on this one is, right? Since now I have a smaller volume, the pressure's gone up. The pressure in the lungs is greater than the pressure outside. And so we can see from these blue arrows that the gas gets breathed out. So Boyle's law is very important and basically tells us how we ventilate. Now, Dalton's law of partial pressure is very important in terms of gases. I'll just kind of give you a problem we could do in lab here and kind of show you the effect of it. So if we took a box and put a separator in between two sides of the box, and put different substances in the box, but in one box, which we're the only thing we're going to be concerned about, and one side of it we had 20% oxygen, so the other 80% was some other gas. And in the other side, the bottom side we'll call it, the bottom half, we have 50% oxygen. And so we have this middle layer that has, let's say, a semi-permeable membrane in it, so semi-permeable membrane. And then we allow the gas to do whatever it wants to do, right? Whatever gas is going to do. And so gas is permeable in the divider now because we've removed the hindrance to the divider, and gas is going to move. And which way will it move? So stop for a second and think about it. And it's not as easy as it first seems. So you think, well, obviously, because I got a higher percentage on the bottom, gas is going to move up. And the answer is not necessarily. And the reason I say that is these values are given in percents. And it's not the percents of gases that drive their movement, it's the partial pressure. So gas is moved according to partial pressure differences, not concentration difference. So having the percentages don't help us. What we really need to know here is what's the partial pressure of the gas here and what's the partial pressure of the gas here on the bottom. The way to do that is use Dalton's law. And Dalton's law, its original form says us that P total, so the capital P stands for pressure, total equals total pressure, equals the partial pressure of gas 1, and this is where it gets confusing, because here we have P total, and this meant total pressure, and here we have P gas 1, looks very similar, but this means partial pressure. So the total pressure of the gas is equal to the partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3, and so on. A similar analogy would be open up your wallet or wherever you keep your money, and the total amount of money you have is equal to the number of $1 bills you have, plus the number of $5 bills you have, plus the number of $10 bills you have, and so on. So the total amount of money is equal to how many you have of each part. Well, that's true of gas. The total amount of gas in terms of pressure is equal to the sums of the pressures that make it up. That's sort of useful, but what's really more useful is this bottom one right here. This bottom portion of the equation tells us the partial pressure of any gas, right? We can figure out if we know the percentage of the gas and the total pressure. So the partial pressure of any gas equals the percentage of that gas times the partial pressure. So in order to be able to apply that idea of partial pressure differences drive gases, you need to be able to use Dalton's law to calculate those differences. So going back to our first problem, right? If I give you more information, it should become obvious which way the gas will go. So if we look at the top one, we said we had 20% oxygen, but let's say our total pressure is 500 there. So my PO2, my partial pressure of oxygen, right, will equal 0.2 times 500. Why 0.2? Because 20% oxygen is 0.2, right? So that's my percent of the gas, 0.2, times 500. Why 500? Because my total pressure, right, here's the equation down here, here is 500. So PO2 equals 0.2 times 500, that's 100. On the bottom one, even though it's got 50% oxygen, we made the total pressure on the bottom box only 100, which means if I calculate this, I get PO2 equals 0.5 times 100, which is only 50. So even though we have 20% oxygen in the top and 50% oxygen in the bottom, the diffusion gradient is actually from the top to the bottom, right? Even though the percentage is 2.5 times higher in the bottom, because the partial pressure is what drives gas, not percentage of gas. So the proper answer when I asked you, if I asked you, hey, which one of these go? I say, I don't know, I need more information, right? I need to know what the partial pressure of each gas is in order to determine which way we're going to diffuse. All right, so here's an example, a couple examples. So let's look at DVC. So at Diablo Valley College, right, we can estimate that the total pressure is about 760 millimeters of mercury. Sometimes that's called a torr, and that comes from a scientist called Evangelista Torricelli. And he was the first person to sort of recognize that air had pressure. And so his thought was, we live submerged at the bottom of an ocean of air. So the farther down you are in terms of altitude in the earth, the greater amount of pressure there's going to be, because there's going to be more air sitting on top of you. Similar to a swimming pool. Some of you might have ever jumped into a swimming pool and gone down to the bottom, and as you get closer to the bottom, you can feel more pressure on your ears, because the farther you go down, the more and more water that sits on top of you. Okay, so since DVC is pretty close to sea level, and the average atmospheric pressure total at sea level is about 760. It depends on weather and other conditions, but about 760. We're just going to assume 760. I didn't check today, but I checked last week for a different thing, and the total pressure at DVC was 755 millimeters of mercury. So 760 is not a bad estimate. And again, that's like 1 atmosphere. That's kind of the standard value. So to figure out the partial pressures, right, we need to know what the percentages are. So the partial pressure of nitrogen, so capital P, capital N2, so the partial pressure of nitrogen, is about 79%. It's sort of a misnomer. The actual percentage of true nitrogen is 78% on Earth. Nitrogen is considered an inert gas, inert. Inert means that it has no biological activity, which is, again, a misnomer. But they also include in that 79% the other gases that make up important gases on Earth that just don't react with the human body. So typically helium and hydrogen and argon and neon and things like that. So these inert gases that have really little or no effect on the human body, when you add them all up along with nitrogen, which makes the vast majority of it, you get to about 79%. The partial pressure of oxygen is about 20.93% in the air we breathe, so 20.93%. The actual percentage of CO2 in our air that we breathe is like 0.04%. Okay, this is already in a percent. So 4/100ths, right? 4/100ths of a percent. It's basically nothing. So once we know those values, and those values you should memorize because they come in handy and important on exam situations. So we take the partial pressure, the percentage of the gas, right? 79.79 times the total pressure, 760, and we get this partial pressure. So the partial pressure of nitrogen is about 600 millimeters of mercury. The partial pressure of oxygen, 20.93 times 760. It's about 159, pretty close to 160. And the partial pressure of CO2, which is 0.04, right, percent. So to put it in decimal form, we go and move the decimal twice, right, to get it from percent into normal value. So 0.0004 times 760, which gives us a partial pressure of 0.3 millimeters of mercury. So that's an important value in order to calculate the partial pressures at various altitudes. So to kind of look at a difference, let's go up to 9,000 feet, okay? So at about 9,000 feet in the French Alps, you know, they still have people that cycle and do tours and other things. But, you know, it, again, depends on a lot of factors. But at normal total pressure you might see at about 9,000 feet is about 570 millimeters of mercury, okay? Why is the total pressure less? Well, since now we're 9,000 feet above the Earth's surface, you can kind of think about it this way. We have 9,000 less feet of air sitting on top of us. Since there's less air on top of us because we're higher up, sometimes they call that thin air, right? Because we're higher up, then the total pressure is less. So once we know the total pressure, the percentages of nitrogen, oxygen, and CO2 don't change. It's just in our atmosphere. It's just the total pressure did. So now we take 0.79, just like we did before, but this time times it by 570, not 760, because 570 is the total pressure. So now we get 450. So as I was saying, we get 450 millimeters of mercury for nitrogen, 20.93. So 0.2093 times 570 is about 119. And for the CO2, the 0.04 again is 0.0004 times 570. So that's 0.23. And these are important because it's the partial pressure that drives gases. If we have less partial pressure, we have less drive to move gas. So let's continue and go up to about 18,000 feet. 18,000 feet is interesting for a bunch of reasons, but at 18,000 feet, that's about the limit where humans can kind of spend a lot of time and you know, pretty much live. You can't get any higher than that. But what I think is useful for us is the total pressure is about 380 at about 18,000 feet. Why 380 is important is it's exactly half of 760. So again, we'll do our calculations. 0.79 times 380. If you remember, that was 600 when it was 760, so it's 300 for this. 0.2093, right, for oxygen times 380. Remember, it was almost 160. Now it's 79.5. And then the 0.004 times 380, that was 0.3. Now it's 0.15. So as you can see, as we move higher and higher in altitude, we have less and less oxygen available. Okay. Now let's get up to Mount Everest. The top of Mount Everest is almost, 29,000 feet, almost 30,000 feet. It's the highest point on the Earth's surface where there's land. And it depends on, again, the weather and time of year and stuff, but the total pressure up there is about 225. Now, again, you just do the calculations we had, and I want to call your attention to this one, 0.2093 times 225. Now, this is a big problem because you notice the total pressure for oxygen, sorry, the partial pressure for oxygen is 47. And we're not going to get into it, but part of the total pressure is water vapor pressure. And so that takes up some room. But the key to remember for this is we'll just use 50. Humans need a minimum partial pressure of oxygen to live of 50. And at the top of Mount Everest, it's not 50. And very few people have scaled to the top of Mount Everest without the aid of supplemental oxygen because of this. As a matter of fact, some of those more famous tragedies that happened up there, at least are in some part attributed to guides and other people climbing to the top of Everest without supplemental oxygen, and then maybe not making the best decisions or reacting the way they should because of the lack of oxygen they might have had. Now, I'm not sure how well that's established one way or another, but that's just at least has brought up some questions because of that. So humans can't live at the top of Mount Everest, right? There's a couple humans can go to the top, but most humans can't because it's below that 50 minimum millimeters of mercury pressure. So that's an important consideration. So this gets into that idea, kind of summarizes the partial pressures we've calculated, 159, 119, 80, 47 at the different altitudes as we move up. And again, this makes the point that the minimum PO2 to sustain life is 50. And most people can't reach the top of Everest without supplemental oxygen. So that's the value of Dalton's law, or sometimes known as Dalton's law of partial pressures. Now, this is the last gas law we're going to talk about for this section, I think. Yeah. This is called Henry's law. And when I was in graduate school, I had a physical chemistry course. And we spent a considerable time talking about Henry's law. And I spent a considerable amount of time not understanding anything. But neither did my classmates, I don't think. And I just remember, I think the first exam that was on Henry's law, I got like 31 out of 100. And that was one of the higher scores in the class. So, it's kind of difficult, but I'm going to summarize it for you. And it's another one of those things that's just, learn it and accept it and be able to apply it. So, and the application of it is so much easier than the information involved in it. Okay, so you'll see. So Henry's law tells us the partial pressure of a liquid will equilibrate to that of a gas that surrounds it. So the partial pressure of a liquid will equilibrate to the partial pressure of the gas that surrounds it. So if we took a liquid and put it in a beaker, right, where the air above the liquid line had a partial pressure of 100 millimeters of mercury. Eventually, the partial pressure of that liquid is going to equilibrate to that of the gas, and the liquid will also have a partial pressure of 100 millimeters of mercury. So Henry's law is important for us biologically for a number of reasons, but one of them is, I think most of you realize that fish need to breathe, and that fish have gills, and their gills are modified pulmonary organs that help extract oxygen out of the water. And so Henry's law, right, puts oxygen in the water because the partial pressure of the water will equilibrate to the gas that surrounds it. So as an example, if you went out and looked at the ponds out by the ATC building, and he said, okay, what is the partial pressure of oxygen in those ponds? Assuming there's no weird things happening with biotic stuff where, there's no organisms, producing or using an excessive amount of oxygen. Well, how would I know that? Well, you could easily estimate it going, okay, since we're at sea level and DVC is 760-ish millimeters of mercury total pressure, and I know that oxygen is 20.93% normally in terms of room air. So if I multiply 0.2093 times 760, right, I get 159. Since Henry's law tells me the partial pressure of the liquid, of the pond, will equilibrate to that of the gas that surrounds it, that's the atmosphere of the oxygen that's just floating around the campus, right? Then that tells me that the partial pressure of the pond should also be 159 millimeters of mercury. So it's a nice application for Henry's law. The other really nice application of Henry's law, and this works for any gas, right, whether it's oxygen or CO2, okay? And we'll come back to that idea. Well, I might as well talk about it since they're here. So one of the things, though, in terms of Henry's law, is just because the partial pressure is the same doesn't mean the amount of that substance is the same. So here's a good example of that. The partial pressure of oxygen in the room air, in this case, is 100 millimeters of mercury. And the partial pressure of oxygen in the solution is 100 millimeters of mercury. But the actual concentration of oxygen is much, much less in the water. But if we look at CO2, we'll see that the partial pressure of CO2 in the atmosphere is 100 millimeters of mercury. And when it equilibrates in the liquid, it's also 100 by Henry's law, of course. But if we look at the concentration of CO2, it's got, 60% or so of what we had in the room air. While again, going back here, those, 12% or something, 13% there. So why is this such a small percentage with oxygen than it is CO2? Well, there's a number of factors that matter, and one of them is the final actual concentration depends on the pressure gradient and the solubility. And so there's more CO2 in the solution than oxygen because CO2 is like 20 times more soluble than oxygen in water. So we're going to see more CO2 because of that solubility difference. And that has implications when we talk about how do we move blood around our body and how do we move oxygen in that blood and CO2 in that blood around our body. And that solubility CO2 will play a role in what we talk about. So the partial pressure of a gas, right, and we'll talk more about partial pressures in the next section, but partial pressures are important in terms of being able to move gas from certain parts of our body and get gas where we need it to go, whether it's inside our body for oxygen primarily or outside our body for CO2 primarily. So as an example, right, the air we're breathing in, let's say, again, at sea level is 159 millimeters of mercury for the PO2, partial pressure of oxygen. And as we breathe it in, into our alveoli, that partial pressure drops, okay? So P, capital A, O2 equals the partial pressure of oxygen. The capital A means alveolar. So in our alveoli, it goes down about 105. And the reason why is even though we're breathing in 160 almost partial pressure, oxygen is always leaving our alveoli and going to the blood, and it's being replaced by CO2. So the partial pressure of oxygen in your alveoli goes down a little bit because of that. So let's say it's starting out at 105. Well, the alveoli, that's a gas, right? And the blood, that's a liquid. So as the blood goes and travels in close contact with the alveoli, then we can apply that Henry's law to this and say, oh, the partial pressure of the liquid, the blood, will equilibrate to the gas that surrounds it, the 105 of the alveoli. So once blood exits the alveoli, its partial pressure will be 105 millimeters of mercury. So it's really, really simple. Is once you know what the alveoli are, you know that it's going to be the exact same number under normal circumstances for the blood. Okay, so for CO2, right, the CO2 comes in at 45, the alveoli is 40, So CO2 is going to leave, right, until it reaches equilibrium, where it's going to come out at 40. That's because of Henry's law. So we can look at that for the tissue and everything else, but we'll save that for the next video.